Hi, everybody. My name is Dr. Nuralari, and I'm a senior lecturer, a program leader here at University of Lincoln, United Kingdom. Today, I'm going to present our paper entitled "Energy Efficient 3D UAV Trajectory Design," and this is for data collection in wireless sensor networks. This is a joint work with Dr. Bonilla and Professor Gogo at University of Rabat, Morocco, and of course with me based in Lincoln. Right, so I'll go through first of all a quick introduction. What is this about? So what we consider in this paper is a wireless sensor node network that is composed with several nodes, and there is a UAV which helps to collect data within that network. So of course the UAV is tasked periodically to collect data on fly, and will deliver this to a control center or a fusion center. The figure in here, it is really a schematic communication. And as you can see at that particular snapshot, the UAV is serving a subset of those sensor nodes, and that is the coverage area required. Right, so the next thing that I want to go through is the system model. And first of all, we'd like to detail our air to ground channel model. So the first equation that you see in there is the power loss between the jet sensor node and the UAV. And obviously this is a well-known equation, no any surprise on that. But what is important of that equation is that eta j, it is a binary random variable, and that binary random variable actually models the path loss, and we'll have two binary values, eta l, if there is a line of sight between a UAV and a particular jet sensor node, and it will be eta n otherwise. Looking at that, easily can be shown that probability of line of sight between the jet sensor nodes and the UAV is given by equation 2. Again, what is important in equation 2 is that this probability, of course, depends on the vertical and horizontal movement on the drones. And of course, A and B are some environment-specific coefficients which are taken to be constant in here. In terms of the dynamic model of UAV, we assume a UAV to be a quadrature, and to simplify the problem, we restrict both the phi and theta to small values. This will allow us a simplified dynamic model, but also enable us to capture interesting parameters in terms of communication systems. So again, this is a state-space equation. The control signal U of t, of course, depends. It is split in ux of y, ux, uy, as uz of t, and for the energy consumption, we assume a single integrator model. Right. So how do we task the UAV to collect the data? So first of all, we assume that every tour the UAV collects some data. It not necessarily need to be at a particular tour the UAV to serve all the network, and the UAV does so by following a 3D trajectory passing through those key predetermined stopping points. As a design problem, as a design parameter, in this paper we are going to actually derive how one can really estimate or predetermine those key stopping points so that an optimum criteria is maintained. Then once the predetermined stopping points are in place, the UAV will visit those and hover at each of those points and will collect data. Now at each particular point, of course, will show next that the UAV will have a certain coverage area. As I said, not necessary to cover or maximizing the number of nodes covered, but our optimum criteria is something else, which I will show on the next slides. And we want to make sure that the tour is a closed trajectory. So basically it starts and stops at the same point. Now, in terms of the sensor nodes, we only allow sensor nodes to transmit a UAV that have the maximum SNR, and this is simply ensuring that quality of service is maintained. For example, if a particular sensor node is set asleep and not transmitted a particular tour, then perhaps on the next tour or so, the particular sensor nodes will be served by that UAV. And again, we don't allow retransmission mechanism, and the packets have a fixed size. Right, so the next thing is, what is the optimality criteria that we adopt in this case? For this particular paper, what we have proposed is to optimize the energy efficiency of this data collection trajectory. And this optimization problem, what it ensures is, first of all, it maximizes the efficiency, and the first term on that first line is the efficiency, and the second one is the penalization term, which assumes that the energy consumption is bounded and allows us to carry out the optimization. So really, it is a mathematical term and not much in terms of the optimization. Now, the constraints ensure that the UAV passes through all the case stopping points in predefined order, as we previously said, hovers at each stopping point until all corresponding sensor nodes have transmitted their data, and of course, obeys the dynamic model. So looking at that optimization problem, it is very difficult to find an analytical solution. And again, it is not permissible to use that optimization problem in terms of the wireless sensor network, because obviously you would require extensive power capabilities and processing capabilities on board to always try and find those predefining points and also the trajectory. So what we propose is a suboptimum solution. And again, this suboptimum solution will show that performs really well, and it will enable us to get the analytical solution in a closed form. So the first thing that we need to do is we derive the trajectory, and then we predefine or estimate the case stopping points. So the trajectory is divided in two vertical and horizontal movements, and these are represented as tau h of k and tau v of k. And of course, by doing so, this will enable us that the dynamic model that we proposed, that we presented previously, is now, it is linear with respect to the control signal u of t. This will allow us to get an analytical solution, insight into the problem, and how this trajectory is dependent or related to those case stopping points. Because as you increase the case stopping points, the trajectory will be different, but obviously we'll see that there is a trade-off between how many stopping points you need and the efficiency of the energy consumption. So by doing that, then we'll be able to come up to a closed form solution of the control signal. And of course, the control signal is divided both on horizontal movement and vertical movement. And obviously, as you can see, these expressions are in a closed form solution. However, what is important is that we now, using these previous derived horizontal and vertical control signal, we'll be able to calculate the energy required for those vertical and horizontal movements. And what is important in this is that it is a very interesting result, actually, and we'll show this on the simulation. But what it is important is to see that the energy consumption in both horizontal and vertical movement are really large if the translation movements are fast. It is say that TH and TV are really small, and of course TV and TH stands for total time spent on that vertical movement. Now, of course, this is very interesting. Some other current state-of-the-art paper assumes or adopt as a minimization procedure equivalent of minimizing the time flight required to perform a tour, and obviously assuming that this is straightforward, directly translated to indeed energy consumption minimization. This is not the case, and it's a very interesting result, and that is the main point of our results in this paper. Again, this demonstrates that the signal processing community need to adopt more realistic models when you deal with such a problem, especially with the 3D UAV trajectory. Once we have the trajectories in there, it is important to obviously estimate or define those stopping points. And of course, we propose here two different methods, as you can see on those graphs. Different trajectories, different method will have different trajectories. The one on the left will allow to have different altitude, while on the one on the right assumes that the altitude is the same. Obviously, this saves energy in terms of energy consumption. You don't need to go up and down. In terms of the results, we consider the wireless sensor network with 120 sensor nodes, and they're deployed randomly in the square region of 140 by 140 meter. These are the UAV parameters, and for the channel model, we assume a dense urban area. We compare 4 different suboptimum trajectories with where the altitude of the stopping point, you remember the previous slides, in terms of the altitude in here, will really define how much energy consumption is required and what it is optimum in terms of energy efficiency. So those are the ZKs in there, 4 different scenarios that we'll plot and compare. And of course, the ZM is the ZM in that case, it is the altitude that maximizes the coverage area, while ZK is indeed, Zm of k is indeed the minimum number of stopping points, altitude, such that the UAV maintains the full coverage. Obviously, there's a trade-off between maintaining the maintaining the minimum altitude so that the coverage area is maintained, but also maximizing the data collection in terms of network coverage. Now, these are the results presented for 4 different scenarios stated previously. As you can see, the case where ZK is really optimized is the curve in red, is really gives us the maximum efficiency, maximum data collection, but also requires the minimum energy consumption, which is the right lower hand corner subfigure. In terms of the coverage is maintained the same in there, and the blue curve is actually worse in terms of efficiency and the data collection, and the blue one is case 3, which is simply a planar trajectory, where ZK is simply Zm, just maximizing the coverage. So maximizing the coverage only does not really gives you the best data collection and best energy efficiency. Right. So again, these figures are versus stopping K point. As you can see, there is an optimum number of stopping points that that will give you better performance. And again, this is not this is an interesting result stating that as you increase the number of stopping points further, you might not get better results. Obviously, we have considered, as a conclusion, we have considered importance of considering UAV models. Minimizing the flying time of UAV is not equivalent to minimizing its energy consumption. I will address this further. So thank you very much for your attention. So if you do have any question, please feel free to contact us or during the session. Thank you.